a fairly large chunk of what analysis concerns itself with problems related to convergence and continuity. So it's pretty important that we become familiar and we understand what these concepts entail. Before we do so, I want to talk a little bit about infinity and how it plays havoc with our intuition. When we deal with infinite sequences of numbers, intuition actually very often fails. Consider the first example. No doubt you've heard about this before, Zeno's paradox. Achilles, the Greek hero, finds himself 100 meters away from a turtle. Let's say that he runs 10 times as fast as the turtle walks backward. So, in the time that it takes him to run the 100 meters, the turtle will have moved backward 10 meters. In the time that it takes Achilles to run the remaining 10 meters, the turtle will have walked backwards an extra meter. In the time that it takes Achilles to run that extra meter, the turtle will have walked backwards 10 centimeters. At no time can Achilles overtake the turtle. Now we know that's not what happens in reality. In reality, if you run or walk 10 times as fast as somebody else, you will overtake them quite quickly. What is wrong with our reasoning? Here's a second example, which we might call the Anti-Dorian Hero. Consider a right-angled triangle. I'm just going to be drawing the width, the base, and the height here. It does have a hypothesis C, and we know from the theorem of Pythagoras that a squared plus b squared is equal to c squared. Perhaps one of the very first things you learned related to mathematics back in elementary school. Now consider the following. I'm going to take the midpoint of the segment here, the base, midpoint of the height, and I'm going to build this one here. This is well drawn. It isn't, but let's pretend it was well drawn. Draw this figure. You will agree with me that the length of the blue path is in fact equal to the length of the red path, right? Because this is because this point is the midpoint. The first half in blue and the second half in blue cover the same distance as the base, and similarly for the height. All right, so now I'm going to take the midpoints of each of these segments, this thing. The length of the yellow path is also equal to the length of the blue path and the length of the red path. So let me do this a few more times. Drawing is not ideal here, but let's pretend that it was better drawn. The length of the green path is equal to the length of the yellow path, is itself equal to the length of the red path and the blue path. If you were to continue this indefinitely, you would get this line here. My staircase keeps on getting closer and closer to the hypotenuse. Now, what's the length of the red path? Length of the red path is just a plus b. It's the length of the hypotenuse, c. So this would seem to say that a plus b is in fact equal to c. And that doesn't match our understanding of right-angled triangle. What's wrong with this argument? We'll do two more examples. An example of an infinite sum. Let S be the following sum. 1 plus minus 1 plus 1 plus minus 1 plus 1 plus minus 1 and so forth. Then you can group the terms as follows. I'm going to group the first and the second, the third and the fourth, the fifth and the sixth, and so forth. So I get 0 for the first pair, plus 0 for the second, plus 0 for the third, always adding 0, gives me a sum of 0. Or, potentially, you could write S as being 1 minus 1 plus minus 1 plus 1 plus minus 1 plus 1 plus minus 1, and so forth, right? Take the 1 out, take the minus the common factor, the expansion. So I'm left with 1 minus S. This is exactly the same as the original S. If S is equal to 1 minus S, that means that S is equal to 1/2. But I could also write it as s is equal to 1 plus, and I have minus 1 plus 1 plus minus 1 plus 1 plus minus 1 plus 1, so forth. And that gives me 1 plus 0 plus 0 plus 0, so forth, which means that it's equal to 1. So I end up with s being simultaneously equal to 0, to 1/2, and to 1. What the heck's going on? How is that possible? Last example. This will be the following sum. We're adding successive powers of 2. Well, I can write it like this. 1 plus twice, take out a common factor of 1, and I'm left with 1, 2, 4, 8, so forth. Again, successive powers of 2. Which is to say that s is equal to 1 plus twice of this thing here, which is exactly s. If you solve for s here, you will get s is equal to minus 1. You are adding positive terms together indefinitely, and then you get a sum which is negative. Does any of this make any sense? Where has our reasoning been in error? You know what all these things have in common? What they have in common is the dot. That is what is wrong with our reasoning. We're using the dot to represent an infinite process, a shorthand for something that continues without ever stopping. We're using the dot as shorthand for the infinity. We don't really know how we can use things, in particular how to use infinity. We are misusing them, and we end up with results that make no sense. These aren't really paradoxes. There's a resolution, and the resolution is we need to figure out exactly how to deal with infinity. The topic of this chapter.